today from Aberystwyth University. He's also doing the work on randomized algorithms and mutation rate that we had already talked by Per Christian Lechre a couple of weeks ago. We also had June Hair in September. So we are now let's start our first talk, and we have actually quite flexible time scale. But we also will have another talk later today by Stefan. Okay, so thank you.
Thank you very much for the kind introduction. Being the first of two speakers is obviously a difficult job, because you don't have to be so boring that you scare the audience away, and you don't have to be so entertaining that the second speaker is having a hard job. So I try to be less boring than you fear and more boring than my usual entertaining stuff. I am from Aberystwyth, which is in Wales, which is a place which is still more beautiful than the surroundings here, with fewer choices for lunch. Aberystwyth University, well, 7,500 students, established in 1872, and our department has about 600 students, and we are doing research in intelligent robotics, bioinformatics, and artificial intelligence, and that's the group where John here and myself are from. So what I'm going to talk about today are randomized search heuristics. And when I say randomized search heuristics, I may be referring to something very simple, like local search, where you have a current search point, and then you consider your neighbor, which are in a well-defined neighborhood, and if you discover a neighbor which is better than yourself, and within this talk we're doing maximization, so higher up is better. If you discover a neighbor which is better than yourself, then you switch to that, so that is local search. You could do simulated annealing, which is almost the same. It's just that you have a probabilistic rule of sometimes accepting even worse search points than where you're currently at. You could be talking about evolutionary algorithms, which have mutation, which allow you to make steps which are slightly larger than just within your neighborhood. And they introduce a different kind of variation operator, which is called crossover, which is based on at least two search points, which you combine in some random fashion to generate a new one. Randomized search heuristics could be artificial immune systems, where you have typically mutation operators which tend to favor large mutations if you are currently at a search point which is bad, and tend to favor smaller mutations when you're at a search point which is already quite good. And you could be talking about arm colony optimization, where your search in the search space is in some way pheromone driven. So this is the space of algorithms I will be talking about. And I will be concentrating today on evolutionary algorithms which are mutation based, so it means evolutionary algorithms without crossover, and artificial immune systems.
So this is all randomized heuristics, randomized search, different kinds. So we have a Xin-She.
Yeah, where is he?
I don't know. He wrote a book on this, what he calls nature-inspired algorithms. Xin-She, yes.
Yeah. Okay, what I'm doing in the field is I'm doing theory of randomized search heuristics, which is difficult because people who are using randomized search heuristics are typically interested in applications and not so much in theory. Critique that you are met with when you say you're doing theory of randomized search heuristics is that it's self-contradictory, because if you are able to do a good theory, then you do a good theory-driven algorithm and do not use randomized search heuristics. Other people say it's plain impossible to do theory, but something which you haven't well understood, and if you understood it very well, then you wouldn't be using randomized search heuristics. And still others say even if you could do it, it would be completely useless. Michalovich in 1906 gave a talk where he cited Dave Davis, and I like this quote, I have to tell it. If there's a theoretical result that indicates that the best value of some parameter is such and such, I would never use the recommended value in any real-world implementation of EAs. This is harsh, right? This is as harsh as it gets. So, why am I still doing theory of randomized search heuristics? I believe that a theory of randomized search heuristic can lead to a better understanding of how to set parameters, of a better understanding on what kind of problems we would like to apply randomized search heuristics, a better understanding on what kind of problems we would like not to apply randomized search heuristics, And, being a lecturer, it's way easier to teach randomized search heuristics if you have a bunch of theorems instead of a bunch of rules of thumb. Okay. If you have heard about theories of randomized search heuristics, there are different kinds of theories around. The most fundamental kind of theory are convergent proofs, which are statements that tell you that your randomized search heuristic finds an optimal solution for every problem, and for most problems nobody will be alive to actually see that. There was started in the 70s schema theory for genetic algorithms, which allowed you to make statements like my GA works by processing schemata. And abstract statements like that are kind of difficult to understand what they actually mean, and the problem with schema theory is that people who are doing schema theory make a bunch of predictions which could be proven wrong. The kind of theory that has been leading, I would argue, within the last 25 years is runtime analysis, where you say that for a specific randomized search heuristic and a specific problem, you can predict how long it will take the randomized search heuristic to find an optimal solution, in very much the same way as you do runtime analysis of classical algorithms. I would claim that it is a success story for 25 years now, and this is what I'm going to be talking about for a long time. And more recently, fixed budget analysis has been introduced, saying that for a specific randomized search heuristic and a specific problem, I can predict the solution quality found within a given computational budget. And I will argue that this is not only a new theoretical perspective, but a very useful one. So what I'm going to, I just covered motivation and overview. If you decided that you're not interested in the kinds of things that I'm going to talk about, this is the point of time to leave, because very good, thank you very much. This is what I'm going to cover. I will be talking about evolutionary algorithms first, I will be talking about artificial immune systems later, and then I will finally come to a take-home message and formulate a few open questions. So let's talk about evolutionary algorithms. The idea of evolutionary algorithms is to understand the process of natural evolution as an improving process, and then you mimic it algorithmically so that you hope that you have an algorithm which is an improving algorithm, and then you obviously do an optimization. So fitness for an environment, it translates into a fitness function, which is your objective function. An individual is a search point, a population is a collection of search points. Mutation means that you randomly change your search point. Recombination means that you randomly create new search points based on existing ones. And selection means that you have a bias when creating and deleting search points towards better or worse.
So,
yeah.
Can I just jump in here? So you here assume that the recombination may happen based on several, more than two existing points?
Yes, at least two.
Okay, that's good, because actually that's what bacteria seems to be doing, because they can pick up bits of DNA from several other bacteria, not from just two, not from one pattern.
Okay. On the algorithmic side, there is a multitude of different evolutionary algorithms. For the sake of the talk, I'm going to be concentrating on the very, very simplest algorithm that I would argue you could still call an evolutionary algorithm. It's designed to do maximization of pseudo-Boolean functions, so functions which map bit strings of fixed length n to reals. We give it a computational budget b, which we just will equate with the number of function evaluations that we allow the algorithm to make. And you have a parameter which is the mutation probability p. And the algorithm is really, really simple. You have a single point in the search point, x, which you select uniformly at random. And then, while your computational budget is not yet used up, you create a new search point y by means of mutation, where for each bit in the bit string independently, you decide with probability p to flip this bit. And then you do a very simple deterministic kind of selection called plus selection, where you compare the function value, the fitness of this new search point to the one of the current search point, and if the new search point is at least as good as its parent, then that's a y, not an x. Then it replaces its parent, otherwise you stick to the parent. And that's the algorithm. So it's kind of local search, just that you're not doing local search with mutation.
Can I just say something here?
Yes, of course.
That I actually know this selection strategy. Basically, it's comparing whether the offspring is better than the parent or not. And the interesting thing is that this selection strategy actually does not coincide with fitness function.
In what sense?
Because fitness function is a function defined on points.
Yes.
But the selection is defined on pairs of points.
Yes.
So it's already not, it's not one-to-one match. And actually the selection strategy can change the fitness. Actually there's sometimes you define a fitness function. But when you're doing selection, like tournament selection, it may change completely the actual landscape. So landscape is no longer the fitness function.
Yeah, that's true.
And they're related, but they're not related.
Yes, but I would argue that, for example, maxima of this fitness function relate to...
Of course there's a relation. So, but this is interesting. There's a lot of people seem to actually equate it. It's not exactly the same.
No, I agree. It's not exactly the same.
And because a lot of genetic algorithms use different selection strategies, like tournament selections or some other kind of selection, they unwittingly mix up and do something with the landscape, which is maybe not even known exactly.
Okay. So the mutation that we are considering is called standard bit mutation. This is the mutation operator. You, with the mutation probability P of n, you flip the bit, and with the remaining probability 1 minus P of n, you just copy the bit. So the expected Hamming distance between a parent and its offspring equals n times the mutation probability. And the most recommended choice, if you look in the literature, is choosing mutation probability of 1 over n, which means that on average you're going to flip exactly 1 bit, which makes it even more like local search. And you have a 37% probability of not doing anything at all. And of course the research question is, how do you set the mutation probability? In order to answer that question, we are going to use runtime analysis as our framework. So we consider this 1 plus 1 EA on a very specific function and ask ourselves, how does the expected number of function evaluations that I need to make to find a global optimum relate to the choice of the mutation probability? So I analyze the first point of time, and my current search point is the maximum. And usually I estimate the expectation of this one. So let's start with considering a 1 plus 1 EA with mutation probability C of n, where C is an arbitrary positive constant. And let's consider a well-known and popular example function where the fitness value is given as n minus the Hamming distance between x and a hidden target string. So we want to find a hidden target string, and the fitness value equals the number of bits that in your current search point coincide with the hidden target string.
So how do we know this x star?
It's given, it's a parameter of the function. The algorithm does not know this x star. If you design the function, of course, you need to know the x star. The model that you have in mind is the model of black box optimization, which means the following. You as the algorithm designer do not have direct access to the fitness function. There is no way that you can analyze and study the fitness function. The only thing that you can do is you can decide on search points, and then there's an oracle, if you want to put it like that, that gets as input your search point and delivers as output the function value. In this sense, black box. So the x star, the hidden target point, is hidden in my black box, and my job is to find it based on the function evaluations that I can make. Okay, just to get a feel of what we do, if you want to prove an upper bound on the expected number of function evaluations that you need to make to find this hidden search point, then you can argue that there are n plus 1 different function values that you could have, which correspond to the n plus 1 different Hamming distances that you could have. And that for each of them, you would need to improve your function value, which means decrease the Hamming distance at most once, hence upper bound. And when you sum over all your different Hamming distances between 1 and n, if the Hamming distance is I, then there are I bits which are still incorrect, and this I times C over n times 1 minus C over n to the n minus 1 is the probability of selecting one of those, flipping this, and not flipping any of the other n minus 1 bits. So the reciprocal of that is the expected waiting time for that to happen when you sum up And you end up with n log n, obviously. If you want to prove a lower bound on the expected optimization time, you could argue that with probability, that with some probability at least half of the bits are initially wrong, and that in t steps, on my slide there's a times t here, it's just that it's hidden in the shadow.
Yeah, you can move the screen a little bit.
Okay, so there's a times t here. So we have probability that initially we have half of the bits wrong, which is 1/2, as you know, then you multiply with some t, and then you multiply that with probability of not being done in t steps, which happens if one of those wrong bits you haven't flipped at all. And and this is all very elementary, and if you plug in a good value for t, like n divided by c times ln n, then you get your lower bound of n. Okay. You can actually prove that this holds, this theta n log n bound holds with any mutation probability c divided by n, where c is any positive constant. It is even true when you give the bits importance. If you're just considering the Hamming distance, then you're saying that all bits are in some way equal and have equal importance of 1. We could say that bits are of different importance and get different weights, and regardless of how you set the weights, still for each mutation probability c divided by n, the expected optimization time is of order n. When all weights are equal, you've seen that on the previous slide, then the influence of this parameter c is e to the c divided by c, which hints at the fact that larger mutation probabilities are way more dangerous than smaller ones. And now the question is, does that solve the problem of setting the mutation probability? Are all functions like this, I want to find a hidden function and function values hint me directly to where I want to go? And the answer is no, of course, not all functions are created equal. I have a formal definition of an example function that I ask you to ignore. Don't look at the formulas. Nobody wants to understand that formula within 2 minutes. Let me jump to my example, jump to my image. This is the Boolean hypercube of dimension n. It's a crude visualization of the Boolean hypercube of dimension n. So we arrange the bit strings according to the number of 1 bits. So the all 0-bit strings at the bottom, the all 1-bit strings at the top, and the rest is arranged in that. And then the fitness function points you into the direction of bit strings with exactly n quarter or 1 bits, and once you found them, it points you to the direction of bit strings where the 1 bits are all concentrated in the beginning, and then it leads you down to the all 0-bit string, and the global optimum is the set of all points, more or less, which have a logarithmic Hamming distance to this all 0-bit string. And for this example function, using a mutation probability of c over n, where c is a constant, is a particularly bad idea. If you use a mutation probability which is of order c times log n, ln n actually, divided by n, then this is an upper bound. And the best mutation probability that you can set happens to be ln n divided by 4 ln 2 times n, and then you end up with an optimization time which is O to the n to the 2.361. And if you are deviating from log n divided by n, if you use something which is asymptotically smaller or larger, then you're lost. Then the optimization time becomes super normal. So setting the mutation probability is difficult. Nobody would ever guess that this is an appropriate value, but you cannot see that if you see the function. So setting the mutation probability is difficult. And so far, we had that if you change the mutation probability only by a constant factor, then this doesn't matter so much. But that's not true. If you consider the class of monotonic function, which I would like to define like that. So for 2 bit strings x and y, we write that x is less or equal to y if this is the case bitwise. And we call a function monotonic if for all 2 different bit strings x and y, if x is less or equal to y, then the function value of x is strictly less than the function value of y.
But the problem is that this is a partial order if it's bitwise.
Yes.
But the pre-order induced by values is a total pre-order.
Yes.
So that would not I would say that if you have a distance, you can define distance. I have a definition of also monotonic landscape, and you define it. If Hamming distance reduces, then the value increases.
Yes, but this function, the definition of this function class is slightly different, right?
But
It means that if you compare two bit strings and you only flip, okay, first of all, obviously the global optimum for a monotonic function is the all one bit string. If you have a bit string which contains 1 bits and 0 bits, and if you only flip 0 bits to 1 bits, then you know that the function value increases. And if you only flip 1 bits to 0 bits, then you know that the function value decreases. But if you flip some 1 bits and some 0 bits, then you have no idea what is going to happen. The function value may increase or decrease.
yeah, you can stay with the same sphere.
Yes.
Radius.
And it's not directly related to Hamming distance.
So what is this order? So this order is a pointwise order. So
This defines an order on bit string, and from this
Ah.
on bit strings, and from this partial order. And from this partial order on bit strings, I infer an order of function values. And every function which obeys this order, I call monotonic. Okay? If you do random local search, where you only flip single bits, what's the expected number of steps you need to make in order to find the global optimum of such a function? Any guess?
So if
We do random local search, so we only flip single bits. And then we compare the function values, and if we found an improvement, we go there. How many such bit flips do you need to make in order to find the global optimum?
About half n.
About
n.
n.
What's the length of n?
It's n log n. If you know the coupon collector scenario, where you have n coupons and you want to collect all of them, and you're given one with each of them with probability 1 over n, this is exactly the same scenario. You need to have flipped each of the bits at least once, and then you are there. So for random local search, all of these functions take asymptotically n log n. It's n ln n plus something like that. If you use the 1 plus 1 EA, which had this bit flip probability, and you use the mutation probability of c divided by n for a constant c which is less than 1, then it's also n log n, which is kind of intuitive. If you use a mutation probability of 1 divided by n, so c is equal to 1, then I don't know what the expected optimization term is. I can prove an upper bound of n times the square root of n, but I do not believe that it's tight. But we've tried to prove that for more than 5 years now, with no success so far. And if you have a mutation probability which is larger than 16 divided by n, then I can come up with a monotonic function where the expected optimization time is actually exponential. And that does not only hold in expectation, but with probability which is exponentially close to 1. So even monotonic functions, which are really easy to optimize, I mean they are among the easiest functions for random local search, provide you with an example where increasing the mutation probability just by a constant factor changes the behavior from n log n, which is as easy as it gets, to something exponential. Okay, let's switch gears and go to artificial intelligence.
Can I ask, so these are constant mutation rates. Basic mutation rate is the same.
It's c divided by n, and it's unchanged over the whole run. Yes. Okay.
So you mentioned this fixed budget analysis, but what you're doing here is
still runtime analysis. I'm coming to fixed budget in a bit.
Okay.
Okay. So artificial immune systems draw their inspiration from the natural immune theory. And one of the problems is that there is no immune theory. There is no one immune theory. There are a bunch of competing immune theories. So you could have something simple like non-self-discrimination or clone selection theory, or immune network theory, or danger theory.
I'm sorry. What is this immune theory? So
Okay. We're talking about the natural immune systems of vertebrates. And immunologists are still in the process of trying to understand how adaptive immune responses actually function. innate immunity is more or less well understood. Adaptive immunity is still subject to research. So saying that I want to have, as a computer scientist, I take the point of view that I use immunity as an inspiration to design new algorithms. So in order to do that, I would need to take immune theory and mimic that algorithmically. And the problem is, there is not the immune theory. There are a bunch of computing immune theories. So it depends very much on which book you take up, which kind of algorithm you would end up with. Typical branches of artificial immune systems are artificial immune systems for classification. And the most classical application, obviously, is intrusion detection systems. And you can also have IAS for optimization. I'm going to be talking about IAS for optimization. Depending on the kind of immune theory you look up, you will find different kinds of immune algorithms, and the one that we are going to talk about today is the B-cell algorithm. The B-cell algorithm, let me talk you through that so that you believe that it's a simple algorithm. It has a population size of mu, so we initialize new search points, orbit strings uniformly at random. Then we do something which is called clonal expansion, and that means that for each of our new search point, we create lambda copies, mu and lambda parameters of the algorithm, obviously. So now we have mu times lambda copies. For each of the copies, for the first of the copy, we apply standard bit mutation, just for the first of the copies. But for all of the copies, we apply something which is called hypermutation, which will be explained in the next slide. And then we do our selection step. And in the selection step, we compare the lambda copies that we made of xi only to xi. And we will pick one of the lambda copy or xi itself with the largest function. So in some sense, the algorithm is really, really simple. Introduced by Kelsey and Timmis in 2000. I said it uses hypermutation, and hypermutation is an umbrella term which is used for mutation at a high rate in a vague sense. And many different hypermutation operators are known. Kelsey and Timmis use something that they call contiguous symmetric hypermutations. And I'm going to introduce 3 different variants of them, all more or less similar. The first variant says you pick a position in your bit string uniformly at random. You pick a length uniformly at random. And then you flip every bit from this starting position up to the length, unless you hit the end of the bit string when you stop. The second variant also picks a position uniformly at random and a length uniformly at random, and you start at the position and flip all the bits within your length. But if you hit the end of the bit string, then you wrap around and continue at the front. So this is a non-wrapping version, this is a wrapping version. And the third variant is you pick 2 positions uniformly at random and then you flip everything in between. Okay. Why am I talking about 3 different versions? If you look at this paper by Kelsey and Timmis, it's not clear which version they are talking about. They're just telling you, pick a random contiguous part of the bit string and flip that. And the funny thing about the paper is that at that time in 2003, Kelsey was the PhD student, Timmis was the PhD advisor, and I talked to them separately. And I sat down with them and had them agree with me on a Markov chain definition of their operator. And they were talking about 2 different variants. They were actually talking about 2 different variants of their algorithm. Really funny.
So what is the motivation for the contiguity? I mean, these parameters are selected, the permutation invariant.
Yes.
In general, so how is that different from a random selection of n bits?
Let me come to the first basic analysis, and then we'll see. So if you are 3 variants, right? Not wrapping around, picking 2 positions and flipping everything in between. If you ask yourself, what's the probability that I'm mutating the ith bit in one such mutation? Then for the non-wrapping, and you plot this over the positions of the bit from left to right. So if you do that for the non-wrapping version, then the probability to flip the first bit is fairly small. The probability to flip the final bit is really, really large, 0.5. If you do this round wrapping, then the probability for each of the bits to be flipped is 0.5. And if you do this, pick two positions, then it peaks at 0.5 exactly in the middle, and is really small at the end. So it really doesn't matter. John Timmis, the PhD advisor, had this version in mind. What the PhD student who implemented the algorithms and performed the experiments actually implemented was this version. So what happened was that the operator tended to flip the bits at the end of the bit string a lot. And they've been trying to optimize a function which was real valued, and they considered a binary encoding using standard binary encoding so that the most significant bits are the front and are hardly ever touched. And the least significant bits, they tried around all the time. So for this kind of problem, it happened to work really well. It's just that both of them had no idea why.
It should be obvious. I mean, there's no a priori specification in the design that there is an order on parameters at all. There shouldn't be a most significant and a least significant bit.
Yes, yes.
But were you the examiner?
Pardon?
Were you the PhD examiner?
No.
It sounds like...
Not at all, not at all. Okay, so yes, the two outer variants are obviously biased. This one is biased towards change in the middle, this one is biased towards change to the end. The one in the middle is the unbiased version. I'm not claiming that there's anything wrong with bias. I mean, in their specific application, the bias was a very good thing. It's just that if you do not know that a bias is a good thing, you shouldn't have one. And if you are having a bias, you should be aware of having a bias.
But if it's unbiased, then it's the same as random selection.
Almost. But let me come to that. The number of bits that you expect to flip is linear in all cases. It's more or less n-third for the versions with the length, and for the two outer versions, no, it's more or less n-third for the two outer versions and n-half, but that's not so important. So you expect large mutations, and the probability to flip just one bit is really, really small. It's quadratic in all three mutations. So if you believe that flipping single bits is important to you, then you shouldn't be doing that. Okay, so we assess what contingency hypermutations do that by comparing them with standard bit mutations with the standard mutation probability of 1 over n by using our 1 plus 1 EA and replacing the standard bit mutations by this continuous hypermutations. And when you say, and we are considering the same example function, and if you say this is the same as picking a random bit string, uniformly at random, this is wrong. Because if you're doing this function, optimizing it with just picking random bit strings means you need 2 to the n steps, divided by 2, minus ½ and the reason is that you're picking bit strings uniformly at random, and there's precisely one bit string that you need to pick. And that takes you roughly half of the bit strings to inspect before you stumble upon that by chance. Continuous hypermutations are way better than that. They do it in all three variants in time n square log n as compared to n log n, because you still have this probability of 1 over n squared to do a 1-bit flip, to leave everything intact but just 1 bit. And it's these 1-bit flips that guarantee to bring you to the global optimum in a reasonable amount of time. For the wrapping one and the two position variants, we also have a matching lower bound for the non-wrapping variant we currently don't have approved. Let me present you experiments. So 100 ones, hidden bit string, it doesn't matter which one, bit string length between 40 and 600. So if you consider the wrapping variant and consider the averages of 100 runs, this is the curve that you get. And if you do curve matching just for fun, then say glueplot will tell you that 0.073 n square ln n is a good idea to match.
So the wrapping in this case is just a way of maintaining certain bits within a search structure.
Exactly.
But it is probably suboptimal. I mean, if it's just chosen.
Yes, of course, it's clearly suboptimal.
Yeah.
And the person who was that this is a running time.
This is the number.